We present norm matters, efficient and accurate normalization schemes in deep networks, a spotlight paper in NeurIPS 2018. We examine the role of weights norm in deep neural networks. Our main contributions are: we show that the effective step size when using batch norm is a function of the weight norm. We suggest using batch norm with L1 norm instead of L2, allowing efficient low-precision computation without degradation in performance. Lastly, we show that by fixing the norm in weight normalization, we improve its performance on various tasks. It is well known that batch norm is invariant to the weights norm. Therefore, when using batch norm, what matters is the weight's direction. In the paper, we show that the change in weight's direction is inversely proportional to the squared norm, resulting in effective step size. Using this notion, we were able to mimic weight decay performance gain without applying weight decay, as seen in the red and the blue lines of the figure. This is done by making a correction to the step size using the weights norm of a weight decay experiment. Next, we present alternative norm metrics for batch norm. The common batch norm calculates the average squared deviation, meaning it is using the L2 metric. We suggest using other metrics such as L1, which is the average absolute deviation, or L infinity. Doing so requires the derivation of a normalization term C, which can be done analytically using a central limit theorem approximation. Gitman and Ginsburg showed that L2 batch norm constitute up to 24% of computation time, probably due to the sum of squares and square root operations. Using L1 metric allowed us to reduce runtime and memory consumption while retaining accuracy similar to L2, as seen in the blue and the purple lines of the figure. Another advantage is that unlike L2, using batch norm with L1 norm is applicable to 16-bit precision. Lastly, we improved weight normalization, which is another normalization technique where the weights norm is decoupled from its direction. It is more appealing than batch norm as it requires less computations. In addition, unlike batch norm, weight norm does not assume independence between samples appearing in each batch, assumption which does not hold for problems such as time series prediction, reinforcement learning, and generative modeling. The problem is that weight norm performs worse than batch norm for large-scale vision tasks, such as ImageNet. Understanding that weights norm matters, we suggest fixing the weights norm in weight normalization in a manner similar to common initialization methods. Although bounded weight norm does not close the full performance gap between batch norm and weight norm, it takes us one step closer to achieving this goal and shows again that norm matters.